So what we're going to do now is talk about how Java threads start and run. And we're going to focus here primarily on platform threads. And we'll talk a little bit about virtual threads. When you start a platform thread, many different layers are involved in creating and starting a traditional Java thread, or the platform thread as it's called now. And we'll look at this in more detail later, but basically you have the operating system kernel, you have system libraries, which are typically written in C, like libc, or where the POSIX pthreads libraries live. You have the Java execution environment, the JVM or ART, and then you have threading and synchronization packages. So all these things are typically involved when you make a thread. So first thing you do is you make a new thread object, like say new my thread, and that allocates very little system state. It's just basically an object, like a Java object with a few fields in it, like the name field and the priority field and the ID field and so on. So no kernel resources are allocated when you say new. However, when you call start on a thread, that will actually allocate the runtime stack, which will run in the kernel, if it's a platform thread or a traditional thread. And once the start call is made, then the stack will be created and run can begin doing its thing in the context of that kernel thread. The start method can only be called once per thread. You have to call it at least once, otherwise nothing will happen. By the way, that's another common bug. If you're not careful when you're programming, you forget to call start. Remember I said you could forget to give the code to the thread. That's one common bug. Another common bug is not to call start. Both of those things will leave you scratching your chin, scratching your head. And the Java execution environment will call the thread's run hook method after start creates its stack resources. And the hook method is just where you put your code. Each thread can run concurrently and can block independently. That's the beauty of platform threads. How do we start Java virtual threads? So unlike platform threads, which focus on all the way down to the operating system kernel, because we have to allocate real threads, virtual threads don't have to do that. And so as before, making a new virtual thread, just saying new thread, that's easy. That doesn't take much of anything because there's no kernel resources allocated at all. And then when you say of virtual.start, that also does not allocate any runtime stack or other kernel resources. So those things are not actually created when you start the thread. Instead, they're going to be shared and multiplexed over a pool of platform threads, which is what's called the fork join pool. So that's why it's so much faster to create and start a platform thread, and also why you can have so many more of them, because they don't allocate the resources that are associated with a platform thread. So virtual threads, very lightweight, platform threads, heavier weight. As before, you can only call the start method once per virtual thread object. Also, as before, this will just keep running. After the start creates its resources, the run method will get called back, and it'll do its thing. And each thread can run concurrently and block independently. This is the real innovation that's been made with Java Project Loom, because it allowed these virtual threads to do blocking operations in a very clever way. And that, without going into too much tedious detail, that required major refactoring of the Java virtual machine, which is why it's taken a while to get this integrated into production systems, because they don't want to break everything on the face of the planet when they add this new feature to Java. So it's taking a while to test it all. So irrespective of whether you have a virtual thread or a platform thread or a traditional platform thread, etc., when things start to run, it all works more or less the same. And the idea is you can pretty much run any code within the run hook method. So the code that go here can pretty much be anything. There's often some constraints or restrictions provided by windowing toolkits, which say you can only have certain operations accessing GUI components in a designated thread, typically called the user interface thread, the UI thread. That's the main constraint you'll find in most threading libraries. And in particular, in Android, only the user interface thread can access GUI components. And we'll talk more about that when we get further along. Likewise, virtual threads are suitable for tasks that block most of the time, often waiting for I/O to complete. And that's because the underlying operating environment, the virtual machine, can do a really smart, clever job of managing those threads when they block. Virtual threads are not intended for long-running CPU-intensive operations. They're really intended for I/O-based operations. CPU operations are not what virtual threads are best for. Just use platform threads if that's what you're trying to do. As long as the run hook method hasn't returned, either because it fell off the end or because an exception was thrown that wasn't caught in the context of run, a thread will be considered to be alive. Interestingly enough, the underlying thread scheduler, which can be a combination of either the Java virtual machine, the Java execution environment, and or the operating system kernel scheduler, can suspend and resume a thread many times during its life cycle. So if a thread runs for a very long period of time, it'll probably be suspended and resumed often as it runs. These scheduling operations are largely invisible to user code as long as you, the programmer, apply the proper synchronization mechanisms. As long as you do things like synchronized statements and synchronized keyword and synchronized objects, blah, 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 everything will work very well. It's only if you forget to do that that you'll have problems with scheduling. For a thread to execute forever, its run hook method needs to run in an infinite loop. Now, obviously, it would not be very common to have threads run forever unless you're doing something like nuclear reactor control system or something where you don't want it to ever shut down. But the point is, for the duration of the program, you just have to make sure that you have a loop that'll keep running. And we'll talk a lot more about that, whether that's a good idea. But if you want it to run forever, just make sure it doesn't break out of the loop. A thread is considered dead after run returns. So when run returns, a bunch of things trigger. So for example, here we're going to have a loop, and if some condition holds, we're going to return. So that means the thread will end normally. Thread can also end abnormally if an uncaught exception is thrown. So if we have an error and we throw some exception and we don't catch that exception in the run hook method, then that exception will percolate into the general execution environment and the uncaught exception handler will be called. But that can't really save your bacon. It can just give you a way to report your thread is going away before the thread goes away. And in fact, you'll see for your programming assignment that you get to play around with that. You have to put in an uncaught exception handler. The join method is a method on thread that allows one thread to wait for another thread to complete. And you can think of join, we've kind of talked about this before with some of the examples we gave. You can think of join as what's known as a simple form of barrier synchronization. So you can spawn a bunch of threads and then you go ahead and join, waiting for them to finish, kind of like a horse race. There's lots and lots of examples of barrier synchronization in the real world, and we'll talk about a lot of them when we get to that part of the course. A thread can also simply evaporate. Nobody needs to join with it at all. So in that case, it just disappears altogether. And in either case, after you've joined with a thread or if it simply evaporates, the Java execution environment can recycle the thread resources. And that would include things like the runtime stack, thread local storage. This, again, is especially true for platform threads. Obviously, for virtual threads, they're not giving very much back because they weren't using very much in the first place. The system resources were being multiplexed with the fork join pool we talked about before. So that's the end of our overview of how Java threads start and run. All right.